Hi, I'm going to demo my project, which is classification of facial emotions. I'll be using CNN and SVM classifier. So the goal of this project is to compare if the CNN architecture performs better when it uses only the raw pixels, or if you add some extra information to it, like the hawk features or the landmarks. So, and further we compare this with the SVM classifier and analyze the performance matrix. So dataset that I use for training is the FUR 2013 dataset that contains 35,887 images of facial expressions grouped in 7 categories, mainly angry, disgust, fear, and all these things. This dataset was collected by a lab, and it's a very famous dataset which I used to train my model. So the pre-processing step involves extracting the features for the image, like face detection and face registration. Then transformations are applied on the pre-processed image, and hawk features are extracted and supplied to the neural network. So I'll be using geometric feature-based process for this. So I've explained the image standardization, face detection, and facial component detection techniques in detail. And the CNN models have the following structures: Model A and Model B. So these are basically similar, except that you can see here that there are separate an extra layer of facial characteristic that is introduced in the model 2. It's a fully connected thing. Now for model A, we have a fully connected neural network with k equal to 1024 and feeding the face landmarks and hawk features into a different fully connected neural network. Then I feed this layers into a fully connected neural network with k is equal to 80 to get the output. So model A is shallow convolutional neural network, like you can see here. So this is basically the description of model A. And model B is first fed with raw input into a fully connected neural network with k is equal to 4096, and its output is fed to another neural network with k is equal to 1024. For face landmarks and hawk features, I have fed the input to a fully connected neural network with k is equal to 1024. So basically, both of these outputs are fully connected neural networks. And finally, we get the output, and it uses deep convolutions. So now let's focus on the multi-class SVM classifier. So for comparison of the performance of the SVM classifier, uh, the raw images were fed to the multi-class SVM classifier for training, and you can see the performance matrix here. So for hawk features and uh, face landmarks, for 7 emotions we have 29%, and for 5 emotions we have 34.4 percentage. And when you add more features like face landmarks and sliding window, you get a higher accuracy. So so basically the performance metrics for CNN and SVM classifiers are shown here for model A and model B, and the difference also can be seen. It's very close, except that you can see that the slight variation basically comes when you go with more features and the face landmarks of hog and sliding window. Here you can see 75% accuracy for model B and 71.4% for model A. So this is the best we have achieved using CNN and face landmarks and hog using model B, and that is the best performance achieved using my model. So classification results and basically the comparison of both these models are shown here. The CNN models have a better performance than the SVM model, and the combination of various features like hog and face landmarks and face detection improve the performance like slightly, because as you can see from the performance matrix here. And also due to the deep convolutions by CNN model B, the model gives a better performance in all the cases. The elevation of its performance is up to 4.5%. It can be also observed that the use of hawk features in Model A reduces the performance when faced off with the case where we use only raw data. This could be resulted by a lack of correlation between both the information or an overfitting. So I've also tried out batch normalization, in which there was a slight improvement in the accuracy. So when I try batch normalization, we see that the CNN and face hog and sledding window increases by 16.9 percentage on model B, which was our previous best accuracy observed. So overall, like I could come to the conclusion that the CNN models give a better result than the SVM, because more features such as face landmarks and hog slightly improves the accuracy. And deep convolutional networks are better than shallow convolution networks is one of the other observations which I found, because model B is 75.1%, which is very close to the actual accuracy, which is 75.2%. So basically these are the instructions to run the code, which I'll be showing in a short while. The model is already trained, so I'll just be showing the instruction to train it. And but the training is a pretty lengthy process, so I will not like run it in full length, but I'll be showing the result from a test image. So these are the dependencies that should be installed before running. So it's TensorFlow, TFlon, and NumPy, and also the other third-party dependencies. So these are the two data sets that I used for training. Kaggle FER dataset, as explained before, and also the Dilip shape predictor model. So I'll just go through the so the I'll be running the test on this temp image, which is basically an image as shown here, and we will be calculating the accuracy, and the model will also classify and show the accuracy in percentage. So I will be running it here. So this is how you actually start the training. You run the train.py file with train equal to yes and then evaluate equal to yes. So the training is actually it takes some time, around 15 minutes, so I'm not covering it up, but it's basically it uses the FUR dataset to train. So here you can see that it loads the FUR 2013 dataset and starts the TensorFlow, and it starts training. I'll be just like aborting this process. I will show you like on the previous image like how to run the test. So basically we have to run the predict.py file, giving an argument of what is the path to the image, which is temp.png. So So as it's running, I will just this can be ignored. It's just a slight warning. So as you can see that it has predicted and with a confidence of 98.8%, and the prediction is angry, and it took like 1.9 second for it to run, which was after loading and initialization of TensorFlow. So here you can see, so I've just explained the basic steps of how to train and how to run. So all these have been covered. So going once again back to the conclusions, we can run this on several. I have run it on several other images and observed the accuracy chart, but I've not included the accuracy chart here. But it is highly accurate. So the CNN models like have a better result. It shows a better result than the SVM, and the deep CNNs are better than the shallow CNNs. So this is the conclusion. Thank you.